Okay, class. So the very first thing we are going to do this term is talk about molecular formulas and what can be learned from this. So this entire class is going to be about analysis. And the first step should always be glean as much information as you can possibly get from the molecular formula. So this is what we're going to be doing right from the get-go. But before we do that, first we're going to do just a minor review of some of the stuff that we did in general chemistry. So if you remember back in Gen Chem, there were essentially two formulas that we could determine. The first being the empirical formula and the second being the molecular formula. And so the molecular formula is what we are the most interested in. So the classic procedure for, and this is basically a three-step process, the classic procedure for determining the molecular formula involves two types of elemental analysis. The qualitative elemental analysis, and this is going to determine the types of atoms that are present: carbon, hydrogen, nitrogen, sulfur, etc. And then the second step is the microanalysis, which is the quantitative elemental analysis. So in this step, we are going to find the number, so the percentages of each type of atom in the molecule. And then this will give you the empirical formula. And then once you've got the molecular mass, you can determine if the empirical formula is indeed the molecular formula, or if it is a multiple of the empirical formula. So for some molecules like glucose, the empirical formula is very, very, I think it's CHO, something like this, but the actual molecular formula is quite different. It's a multiple of that. Probably a bad example since I can't remember what that is off the top of my head. But anyway, next slide. Okay, so what we did do in Gen Chem 1 was a combustion analysis. So we would take our sample here, CXHYOZ. We don't know what the relative numbers are. We burn this in excess of oxygen, and we produce carbon dioxide and water. So we have a known quantity of this, and we measure the amount of carbon dioxide we capture and the amount of water that is captured. And we just take we can determine the millimoles of the carbon dioxide, because that's what this is here. Take the measured amount, and this will give us the number of millimoles of carbon dioxide. And because there's one carbon in this molecule, the number of millimoles of carbon dioxide is going to equal the number of carbons in the sample. In the case of water, there's two hydrogen atoms in water. So whatever millimoles or moles of water we determine, the number of moles of hydrogens can be twice as the amount, because there's two hydrogens in each molecule of water. So if we follow these steps, we do the calculation, and it turns out that we can calculate the percent carbon, percent hydrogen, and oxygen is just subtracted from the 100%. So if you calculate this to be 20 and this to be 10, then the oxygen would be 100 minus 20 minus 10, which would be 70. Okay. Yeah, we did this at the very start of Gen Chem 1. So it's nice to do a practice calculation, and after this thing's done, I'll give you one to do. So the empirical formula from the combustion weights. Okay, so if you start, so there is, if you have the percent composition, the simplest way to do this is just assume you've got 100 grams, because if you've got 40, if you know you've got 40.1% of carbon, if you've got a 100-gram sample, this would mean you've got 40.1 grams. And if you've got 6.6% hydrogen times 100 grams, 6.6 grams. Likewise, with oxygen, 53.3, that would be 53.3 grams. You just divide this by the atomic mass. For carbon, it's 12.1, hydrogen, 1.008, oxygen 16. And this gives you the moles of carbon, the moles of hydrogen, and the moles of oxygen. So a ratio would be carbon 3.34, hydrogen 6.55, and you just divide by the lowest, we convert it to the simplest ratio, and you come out with CH2O is the empirical formula. This is the empirical formula for glucose, actually. All right, so the next step is determining the actual molecular formula from the empirical formula. Now, historically, there were a whole bunch of different techniques that were used: vapor density, cryoscopic methods. This is a freezing point depression experiment. All very, the trouble actually with quantitative analysis or combustion analysis is that you have to be extremely precise with measuring stuff. And the slightest amount of impurity will change the percent composition of each thing, which will wreck your analysis. Luckily now we've got mass spectrometry, and this is a super technique which we're going to learn about in the class. And so when you put your sample, which had an empirical formula of C2H20, CH2O into the mass spec, the molecule loses a single electron, so it becomes a charged species, and it gets detected with a mass to charge ratio, which equals the molecular mass or molecular weight. So here, if it was 180, that is 6 times what CH2O would be. So this is just a ratio 6 times that. And if it was 90, then this would be your empirical formula. So mass spec has really allowed this whole process to be far simpler, more precise, more accurate. Just a wonderful technique. But it's still important to know how to do a combustion analysis calculation and that type of thing. Okay, so once we have our molecular formula, then we can determine there's a whole bunch of things that this will tell us. The next part of the course, we're going to talk about different functional groups in molecules when we're talking about infrared spectroscopy. And the formula itself is going to tell you which functional groups are possible, which functional groups are absolutely impossible. The other really important thing is what we call the index of hydrogen deficiency. And this is also known by a couple other things like the unsaturation index, or as I use it, commonly call it the number of double bond equivalents, or DBE. So the simplest of organic compounds just contains carbons and hydrogens. We call these alkanes, and they have a set formula of Cn, and then the H will be 2n plus 2. If there is a double bond in the system, or if the system is cyclic, so it forms a ring, we call the ring system cycloalkanes, and we call anything with a double bond an alkene. This formula switches to CnH2n. So we lose these two hydrogens here. And likewise, if our system's got a triple bond or an alkyne, then the formula changes again. So CnH2n minus 2. So as you add double bonds or as you add ring systems, this formula changes. So if you've got a molecule which has got carbons, hydrogens, X here can be any halogen. So halogens are beside the Nobel gases, so fluorine, bromine, iodine, chlorine. Nitrogens, oxygens. I haven't included sulfur here. Sulfur would be basically the same as oxygen. Phosphorus would be the same as nitrogen, etc. You can calculate the index of hydrogen deficiency by just start with the number of carbons and subtract half the number of hydrogens, half the number of halogens. You add half for each nitrogen plus 1 at the end. Here's another simplified version of the formula. And this will tell you the number of double bonds in the system or the number of rings. And this information is again going to help you determine which functional groups are actually possible within your molecule. So if you've got a double bond equivalence of 4, this could be 3 double bonds plus a ring system. If you've got 2, then it would be 2 double bonds or 2 ring systems, or a double bond and a ring system. And so when we go through the functional groups, what you're going to see is that certain functional groups are what we say completely saturated, so they have no double bonds, and other functional groups have double bonds. So this should always be the very first thing that we do, is determine the index of hydrogen deficiency or double bond equivalence. So I've got some questions after this little lecture, and you can do a little bit of math and get familiar with these formulas and how everything works. Okay. Right. Now, the last bit of the molecular formula intro is what we call a rule of 13. And this is a fascinating little rule. And so if you know the molecular mass or the molecular weight of your compound, you can determine the base formula of that compound by the rule of 13. So what you do is you take your molar mass and you divide it by 13. This will give you typically a number which, so it's going to give you the number of nitrogen, a whole number. So let's say that if we've got for example, let's use, say you've got a molecular mass of 100. Let's get out a little something to draw. Here we go. Okay, so say you've got a molecular mass of 100. You divide this by 13, and 100 divided by 13 equals, this equals 7.6923, goes on and on and on. So this will equal, this would be 7 plus r divided by 13. So the fraction is r divided by 13. So let's subtract 7 from our thing and multiply what's remaining by 13. And this would be 9/13. So on my calculator, basically I just removed 7. So I had 0.6923 and I multiplied by that by 13, and that came up to number 9. So this is basically the formula. So our base formula for this molecule would be C7H 9 plus 7 is 16. And you can check that if this is actually correct by just taking 12 times 7, which is 84. So carbon's got an atomic mass of 12. Hydrogen is 16. And so 84 plus 16 equals 100. So this will give you the base formula. And then if you know that there's an oxygen in there, you can substitute in an oxygen by just taking out, say, atoms which equal that of oxygen. So let's say that this was our base formula and we had 1 oxygen in there. So oxygen's atomic mass is 16. That would mean that we would have to remove a carbon, which equals 12, plus 4 hydrogens. Because 12 plus 4 is 16, right? So this would mean our formula would then become C6H10 That's an ugly 6. So it's like if you need to add an oxygen to your thing, you have to make sure you maintain this 100 as your final, as your molecular mass. So that's the only trick to the story. So we're going to be using this a lot, the rule of 13 to get the base formula, and then we can figure out if there's other heteroatoms, so atoms that are not carbons and hydrogens, so oxygen, sulfur, a halogen, nitrogen perhaps. Another interesting note is that if you've got a nitrogen in your molecule, the rule this molecular mass is going to be odd. So if you ever see a molecular mass that is odd, that's a hint that you've actually got a nitrogen in your compound. And when we do the mass spec section of the course, we're going to see that certain elements, particularly bromine, chlorine, have got two isotopes that are important in the overall mass of that atom. So we'd have to use either the lighter mass or the heavier mass, but we'll get to that when we get into mass spec. So we're going to use the rule of 13 quite a lot. It'll be basically the first step of our analysis. We need to know the molecular mass, so we can we're going to get the molecular formula, and we're going to calculate the double bond equivalence. And then from that's going to narrow down the possibilities, and then we will focus in after that on what the unknown might happen to be. Okay, and that's it for this first little section. So the next part, I've got some questions that you can try. And from there, what we'll do is, on our first class, we are going to go through some of the functional groups. And then we will go through some of the instrumentation for infrared spectroscopy. Plus, we'll answer any questions that people might have with regard to this. Okay? All right.